Now, why interpolation is very, very important to engineers? So let me give you one simple example. If you are trying to measure the variation of friction with respect to temperature, let us say you have a few data points where you have measured temperatures and the corresponding friction coefficient, and you want to generalize and understand a relationship between temperature and friction, so that you can utilize that for any temperature in between, because your measurements are pertaining to specific temperatures. So if you want to have a general understanding how exactly the friction is behaving between the two metal blocks with respect to temperature, then what you do, you use those data points and actually fit a curve, fit a polynomial to understand the relationship. And this is also used in optimization. If you want to understand the sensitivity of a parameter, you have to have a curve from which you can reckon your slope, which would serve as sensitivity. Or sometimes curve fitting can help you understand which parameter, that is out of a, b, c, d coefficient for a, let's say, fourth degree or third degree polynomial, which coefficient that is, whether it is the cubic term, whether it is the quadratic term, whether it is the x power 1 term, that is actually making a huge difference. So curve fitting has got several applications. Even in case of data analytics, unless you understand the relationship between any two parameters, you would not be able to analyze that system. So regression or line fitting or curve fitting becomes one of the basic warranted requirements even over there. So what we are trying to do here is we are trying to understand a very, very powerful technique called Lagrange interpolation. If you recall, when we were trying to verify or understand the correctness of the backward interpolation formula, in one of the discussions, we did use the Lagrange interpolation to fit the polynomial and then predict the value at certain independent variable. And then we said whatever the value predicted by the Newton backward interpolation for x equal to 6 was exactly matching with what the Lagrange interpolation curve predicted. So let's try and understand how exactly it works. Here I have got three set of curves. This is a typical example we have chosen from finite element application, where a curve has certain values at certain x coordinates, and we are using Lagrange interpolation to construct that particular curve. Okay, so to construct that particular curve, we are using the Lagrange interpolation. One of the beauties of Lagrange interpolation is that it does not take slope into account. It only takes the x coordinates into account, and then it comes out with the definition for the curve. Now let's look at how it works. For the first curve, what happens? We are saying that x equal to 0, the value is 1. Let us check whether it is able to satisfy that. Put x equal to 0, you get 0.5 by 0.5, which is 1. And again here 1 minus 0 by 1, which is exactly 1. Am I right? So at x equal to 0, you can clearly see that the value of the function is 1. And that is verified by the formula. And whether it simultaneously satisfies other two conditions, let us see. What are the other two conditions? In fact, you can see that at x equal to 0.5 and at x equal to 1 also, the function has 0 value. And also you can check for any intermediate x also. We'll do that. You can see if I put x equal to 0.5, what happens? This becomes 0, so the entire term becomes 0. And if I put x equal to 1, what happens? This term becomes 0, the entire term becomes 0. So at least this fitted curve at 3 significant points, what happens? Gives you correct value of y. The correct value of ordinate is given by this expression. Now let's see. You have fitted the curve. You have checked at 3 important points which are actually given. Now let's see whether you get this particular point, that is y ordinate for x equal to 0.2. Let's see what happens if I check for 0.2. So 0.5 minus 0.2 divided by 0.5, and here it is 0.8 and divided by 1. So what happens? This becomes 0.3 and this becomes 0.24, and then divided by 0.5, that means it is 0.48 approximately. And you can see that this is exactly 0.48 approximately. So that means if you input any value of x along this fitted curve, what happens? This gives you a perfect actual value of ordinate for whatever curve that you have desired. You have desired a quadratic, and you have stipulated that it must obtain value 1 at x equal to 0 and 0 at x equal to 0.5 and x equal to 1, and this is the quadratic curve that you have produced. And you can verify that at every x, so whatever you have plotted is exactly satisfied by this equation. So therefore this equation represents this curve, right? So what is that is required to produce this curve? That is this particular equation. This equation represents that curve. We already verified that. So what is the input needed to construct that particular curve? All that you needed were 3 points. All that you needed were 3 points. What were those points? Say at x equal to 0, your y value was 1, and at x equal to 0.5, your y value was 0. At x equal to 1, your y value was 0. So these were the 3 points that were used, and then you used the standard formula for Lagrange interpolation and got this particular curve. And then when we plotted this, you got this smooth curve which actually satisfies all your requirements. So how did the problem started? We measured for these 3 independent variables. I was giving you the example of temperature with friction. Let's say the friction value is of a certain number at let us say room temperature. Then you increase the temperature, you found that the friction became 0, and you further increase the temperature, the friction became 0. Of course, I have considered a very, very typical FEM case here, but I am just trying to give the analogical description of this. So if you have 3 independent variables at 3 time intervals or at 3 temperatures, if you are measuring the dependent variable, say friction, pressure, or whatever physical parameter, then if you use the Lagrange interpolation, you get this smooth curve fitted through those 3 points. So that means if these stipulations have to be satisfied, that is at x equal to 0.5, at x equal to 1, and at x equal to 0, 1, then this is the smooth possible curve that can be fitted, and that is what exactly the Lagrange interpolation do. Forget about all this. You start with this data, 3 independent variables and the corresponding dependent variables, and use the definition of the standard formula of Lagrange interpolation, and you get this particular curve. You get this particular curve, and when you plot it, you would be absolutely delighted that you would have satisfied all these 3 criteria. When independent variable is 0, your dependent variable is 1. When independent variable is 0.5, your dependent variable is 0. When independent variable is 1, your dependent variable is 0. So this is the beauty of the Lagrange interpolation. Now, incidentally, we'll also discuss the other 2 curves, just to give you that confidence that even if you change your values, how exactly it works. Here you are saying that your independent variable is 0, and your dependent variable is also 0. This is 0.1. You can see it is perfectly verified. You are saying that your independent variable is 0.5 and the dependent variable is 1, and that is also satisfied because exactly at the midpoint x equal to 0.5, your y value is 1. And you are again saying that your independent variable is 1 and the dependent variable is 0, and this is the point I am talking about. So this is the only smooth curve, even if you practically investigate possible. Of course, you can have several curves, but the smooth continuous curve, if you want to fit, this is the one that you would fit. And what about the last one? The last one also is quite easy. If you want the last curve to be fitted, what are the criteria? you are starting with 0 independent value of independent variable. Dependent variable is also 0. The next is you're talking about 0.5 independent variable. Dependent variable is 0, and you're talking about 1 as the independent variable, and the dependent variable is also 1. And you can see 1 comma 1, and exactly here you see 0.5 comma 0, and here it is 0 comma 0. You can see this is the possible smooth curve that could be fitted, continuous smooth curve that could be fitted here. So therefore the Lagrange multiplication, what it does, it takes into account the x and the y coordinates and then constructs a beautiful definition which actually satisfies all those points and gives you a very good interpolation. Okay, so let's try and implement it for some of the typical university problems. Before we did that, let's look at what exactly is the formula. In most of the university problems, you would not get more than 4 points. For example, here you can see that you have x naught comma y naught. Understand the formula very carefully here. And what about the next point, x1 comma y1? Next is x2 comma y2. Next is x3 comma y3. These are the points that are going to be given to you to fit a polynomial. Now you can see here that y naught is the value when the independent variable is x naught. Y1 is the value of the dependent variable when it is x1. And then similarly, y2 will be the value of dependent variable when the independent variable is x2. And finally, y3 is the value of dependent variable when the independent variable is x3. It has to be understood carefully, and this is the formula. And you can see here that all these points are constructed only using the value of x. And how to remember this? What is the mathematical structure? If you observe the denominator, now this pertains to x naught. The first term pertains to x naught, y naught. There you see the denominator is from x naught you are subtracting all rest of the x coordinate, x naught minus 1, x naught minus 2, x naught minus 3. If you looked at the second one, which pertains to x1, y1, you are subtracting x naught, x2, x3 in the order for the denominator. And here this pertains to x2 and y2, you are subtracting x naught, x1, x3 from the denominator. This pertains to y3 and x3, you can see you are subtracting x naught, x1, x2. Very easy to remember. What about the numerator? Numerator is also quite simple. Since it belongs to x naught, forget about x naught, you subtract x1, x2, x3 from x. And also for the second term, if you see, it pertains to x1, y1, forget about x1, x naught, x2, x3. And the third term pertains to y2 and x2, forget about x2, x naught, x1 and x3. And similarly last one, x naught, x1, x2, forget about x3. And each ratio that you get in terms of defined in terms of x is multiplied by the corresponding y coordinate. That is, first term belongs to x naught, multiply that by y naught. The second term x1, multiply that by y1. The third term belongs to x2, multiply that by y2. The third term, the fourth term rather, that belongs to x3, multiply that by y3. So how many points are required? x naught, y naught, x1, y1, x2, y2, x3, y3. 4 points are required. And you can also see the order of polynomial. You can see that it is a cubic polynomial, because you can see here x cube being produced by almost all the polynomials. Of course, the bottom ones will have certain numerical value because they don't contribute to any x, because all are populated by actual values x naught, x1, x2. There is no x in the bottom. Okay, that's very clear. So if you have 4 points, then you can find out 4 constants. That means you can fit a cubic polynomial, and that's what exactly we are doing. It's a matter of common sense, because if I say y is equal to ax cube plus bx square plus cx plus d, how many constants you need to determine to fit a cubic polynomial? 4. And how many points you are given? 4. So therefore, at the most you are going to deal with in a typical university exam is a cubic polynomial. If you're lucky, sometimes you may get a quadratic polynomial. But this is the standard formula of the Lagrange, and this is used in several applications, even under numerical techniques. For example, finite element method. And the first example that we incepted with is one standard element which is constructed using whose interpolation is constructed using Lagrange interpolation. So let's try and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.